Hello. Good morning, guys. I hope you can join me now. We were having technical difficulties with the meeting previously. I'll wait and see if anyone shows up. Oh, yay. There's Haley. Good morning. Can you hear me? Hi. And hopefully Garrett will join. I don't know what happened with the link, but I'm glad that you were able to join me now. And I can't hear you at all, by the way. Are you speaking? Can't hear you. Something might be wrong with your computer because it's not letting me hear you.
How about now?
Can hear you now.
It was on mute.
Well, that would be why.
Yeah. So the second thing you sent us, that's what worked for me. So I don't know.
I noticed on my computer there was a different code for the meeting than the one on my phone because I have the app on my phone and on my computer, but I always text y'all from my phone. So I don't know why it was like that. So I just manually typed it in.
Yeah.
So today we're going to be on page 391 in your textbook to start out. You're my one who likes to follow along anyway, so I'll tell you where we are. Okay, so you watched yesterday's video, and that talks about Boyles's law and Charles's law. And Boyles's law was relating pressure and volume, and remember they were oppositely related. And Charles's law was relating volume and temperature, and those are directly related. Hey, Garrett. Okay. So we are on page 391, Garrett, in the textbook. And we're going to start with the combined gas law. Remember yesterday, Boyles's law, Charles' law, you do not need to memorize. The combined gas law, you do need to memorize, and we will be doing some problems with it today. So very exciting. Back to our lovely equations. Okay, so we're just going to put them together, and let me just try this really quick and see if I can like write it out for you. Okay, so we're going to put them together, and it's going to be, sorry, this is like, I'm writing with my mouse pad. Okay, so it's going to be, you'll see here how this was Boyles's law, pressure and volume. And then here was Charles's law, volume and temperature. We're just putting it together. So it's going to be pressure times volume divided by temperature equals constant. So what we can combine that to be, sorry, I am learning how to do this, would be, just like we said yesterday, pressure, volume, temperature under one set of conditions equals pressure, volume, temperature under another set of conditions. So this right here is the combined gas law, and this is the equation that you need to memorize. And you'll see that at the bottom of page 391 there. All right, any questions on the combined gas law so far?
No.
Okay, cool. All right, we'll memorize that. The one thing that you do need to remember about this equation is that you always have to use the Kelvin temperature scale. Let's see if I can get this screen to go away because you don't need it. Okay, so always use the Kelvin temperature scale, which we talked a little bit about yesterday. But if they give you a temperature in Celsius, what are you going to add to it to make Kelvin? Anybody know?
273.15.
Yes, perfect. All right, so if they give you a Celsius temperature, you will convert it to Kelvin. If they give you a Fahrenheit, you're going to convert it to Kelvin. The reason being, because you cannot have, remember, 0 degrees Kelvin. No one's ever reached that low of a temperature. And in our equation, you saw volume was on the bottom. I mean, temperature, sorry, was on the bottom. So if the temperature is 0, your fraction isn't going to make sense because if anything's divided by 0, it's undefined, if you remember that from algebra. So we cannot have 0 on the bottom. So that's why we use our Kelvin temperature scale. So just make sure you always do that. And I will go ahead and do an example with you guys. All right, so let's look at example 11.1, and that's on the bottom of 392. And I'm going to share the screen and see if I can possibly do better. Let's see if I can clear this. All right, so it looks like you guys could write on here too if you wanted to. I'm not really sure. I'm still figuring this out. Let me know if there's things I don't know that you know that would make this better, because y'all are smart. Okay, so a weather balloon is filled with helium before it's launched. On the ground, the gas has a temperature of 25 degrees Celsius and a pressure of 1 atmosphere. The volume of the balloon is 4.5 meters cubed. As the balloon rises, the pressure and temperature change to 0.3 atmospheres and 15 degrees Celsius. What is the new volume of the balloon? One thing I did not mention before is your pressure, your P1 and your P2. It doesn't matter what unit they are. Remember, we talked about 4 different units for pressure yesterday, as long as they use the same unit. And the same goes for volume. Doesn't matter what unit you use, as long as V1 and V2 have the same unit. Does that make sense?
Yeah.
Okay. All right, so here, let's go ahead and fill in what we have. So we're going to use our combined gas law here. So we're going to use P1, V1. Oh, there's Kaysen. Hello, Kaysen. We can hear you, but we can't see you. But we don't have to see you. Okay. This is what we're using. All right, so someone tell me from the example what P1 is going to be. What is the first pressure that they give us, our starting pressure, before it's launched?
25.
Do what?
Atmosphere.
Yeah, 1 atmosphere. That was the pressure before the balloon was launched. So I'm going to go ahead and fill that in. Whoops. Hey, Kaysen. Okay, so 1. Why is this not drawing? 1 point. Sorry, I don't know what is going on here. Okay, 1.0 is P1. Okay, what is the volume before the balloon is launched? Who knows?
4.5.
4.5, thank you. I'm gonna go ahead and fill it in. And remember, we're gonna use parentheses. We're multiplying them by each other. Okay, what's our temperature before the balloon launches?
25 degrees Celsius.
25 degrees Celsius, which we're gonna then add, let me get my calculator. What are we gonna add to it? 273.15 plus 25. So that's gonna give me, because I always wanna use Kelvin, that's gonna give me 298. Okay, so we are in example 11.1 on page 392. So that's gonna go on the bottom. So I have my conditions before the balloon is launched. Now I'm gonna fill in my conditions after the balloon is launched. So what is our new pressure? Anybody?
Oh.
0.3 atmospheres. Do you see that in the word problem? It says the pressure and temperature change to 0.3 atmospheres and 15 degrees Celsius. So we don't know volume 2. That's what it's asking me for, okay? So my temperature went to 15 degrees Celsius, which I add 273.15 to, right? Which gives me 288.15. Sorry, this is like so difficult. Okay, now I can just solve for V2. So what will I do to get volume by itself? I'm going to multiply on both sides. Let's see. By the, you can't see here, but the opposite of this. So I'm going to multiply by 288.15 divided by 0.3 on both sides. That way it's going to cancel out over here. Does that make sense?
Yeah.
Okay.
Mm-hmm.
Oops, I didn't mean to put a decimal there. 288.15 divided by 0.3. Which is going to make that cancel, and V2 will be by itself at that point. So let me put it over here. On the top, you're going to have 288.15. Y'all probably don't need me to do this because it's in your book, right? I'm just wasting my time, but I'm going to do it anyway. Okay, so then I'm going to plug it in my calculator, which means I'm going to do 288.15 times 1 times 4.5, all of that divided by, and make sure you use parentheses, 0.3 times 298.15. And you should get 14.49. Do y'all have your calculators? No? Okay. Well, when we do our, you're going to need them in just a minute when we do our practice problems together. All right, so that's our new volume, and here they rounded it to just 14 because we have 2 significant figures given to us in the word problem. All right, next one. Towards the bottom of 393, a gas is stored in a 3-liter container at a pressure of 456 torr. If the temperature stays constant, what will the pressure of the gas be if the volume is decreased to 0.75 liters? Okay, so you would think we're going to use the combined gas law, but it tells us that the temperature stays constant, which means that we don't necessarily need that aspect of the equation. So we can leave temperature out if it's going to stay the same because it won't affect the problem, right? And it tells you that at the bottom there. So instead, we're just going to use Boyle's law. So turn the page on 394 at the top. You'll see there we're going to use Boyle's law because temperature is going to be constant. So we just need P1V1 equals P2V2. What you really need to remember is where pressure, volume, and temperature go. So always pressure and volume on the top of the equation and temperature on the bottom. All right, so if the problem tells us that one of the variables stays constant, the variable will cancel on both sides of the equation, so you don't need it. It will be wasting your time to plug it in. Okay, so now we have an equation. We can plug in the information that we have. So they gave us a 3-liter container to begin with. So what's that going to be? The 3-liter container, 3 liters is what in the equation? Volume 1. Okay, so I'm going to plug in volume 1, 3 liters. Okay, and at a pressure of 456 torr, which is pressure 1, right? 456. Okay. And it says the temperature stays constant. What will the pressure be? So I'm trying to figure out P2. It's asking me for that. If the gas, if the volume is decreased to 0.75 liters, so that's V2, 0.75. Okay, so to get pressure by itself, I'm going to divide by 0.75 over here so that it cancels. And I'm going to divide by 0.75 over here. So in your calculator, 456 times 3 divided by 0.75. And you should get 1,824, which they then put in scientific notation for significant figures. So in your book, you'll see they got 1.8 times 10 to the 3rd torr, and that is your secondary pressure. Do we have questions on these before we move on to doing the ones in our student book? No? Am I frozen? Because you guys look frozen. I'm on the internet. Can you still hear me?
Yeah.
Okay.
Yeah.
Haley,
I'm just putting it on mute so you don't hear my dogs.
that's fine. You all just were frozen and then it said my internet was unstable. So I'm gonna make sure you could hear me.
Now she's frozen.
Now I'm frozen. Can you hear me? Give me a thumbs up if we're all good. We're not good. Can you guys hear me?
There you go.
I'm back. Okay. All right, I'm clearing this. We are going to work on 11.1 in your student book. So plow
And now she's gone.
book. I'm gone. What's going on, guys? I'm right beside the internet. I don't know why it's doing this. Can you still hear me? Hello? Can y'all hear me? Okay, well, it's recording, so hopefully if I post it, you can fill in the missing spots. Can y'all hear me again?
Yeah.
Yes, we just can't see you.
I don't know what's happening. The internet is on. I'm right beside it. I don't know. Okay, well, we're
Yeah,
gonna,
we can see you a little.
okay. I hope that I don't look stupid.
No, you just like it ends in it glitches a little.
Okay,
It could just be my internet.
well, it said mine was unstable, but now it's back, so I don't know. Okay, 11.1.
A lot of people in my house are on the internet, so.
Oh, that could be. All right, everybody got their student book out? Give me a thumbs up. Good.
My Noah thumbs.
What?
Noah and me, Landon and me both have the same thumbs, so we call them.
Oh, how they go backwards like that? Oh my gracious. So weird. Okay. 11.1, go ahead and start working on that. I'm gonna write it out, but you guys can work on it also, because it might take me an hour. I do want you to notice something when you read the first sentence. It says a gas is stored in a metal cylinder with a volume that cannot change. So that means we don't need the volume in our equation, right? So all we're going to use is pressure and temperature. That's going to be your equation. Anybody stuck? Are y'all doing good?
You get like the equation filled out. You divide the top by the bottom of the first set, and then do you multiply it by the second?
Are you following along with me? Are you talking about this original equation here that we were using?
Yeah.
Yeah, so I wanted to get pressure 2 by itself because that's what it's asking me for. So I multiplied by T2 on this side and multiplied by T2 on this side. You have to do the same thing to both sides. And now pressure 2 is by itself. So I'll have temperature 2 times pressure 1 divided by temperature 1.
Okay.
Jason, do you already have the answer?
Hmm.
You already have the answer?
No, I'm still working on it.
You're usually the first one, that's why I asked. Garrett, you got it?
Yeah.
Good job.
I got 33.95 though.
Okay, I did too. It was 3395.53, but we have to round for significant figures. No, it's not significant figures. It's because the temperature, when you find temperature 2 and you add 273.15 plus 30, it's adding, so you have to keep it to the smallest decimal place. So instead of doing 303.15, you would do 303.2. Does that make sense?
Yeah.
So when you plug it in, you should get 3396. Can you guys read this stuff that I'm writing here, or do you want me to try something different?
No, we can read that. Or at least I can.
All right, let's move on to 11.2. Unless Kason and Haley, did y'all have questions on this?
No.
All right, let's move on. Let's do 11.2. We're going to do 11.2 and 11.3. So it looks like in 11.2, you're going to use your combined gas law. So you're going to use pressure, volume, and temperature. Always pressure and volume on the top, temperature on the bottom. Oops, I don't know why I did the 2. Okay. Can you guys write on this too? Do you know? Ooh. So somebody could do it on here if you wanted to. Does somebody want to do this one? Garrett wants to.
Oh. I was just seeing if you actually can.
It asked me for your permission for you to control my pencil, and I said yes.
Okay.
I was able to do that without asking.
Do I have to click on the pencil or does it matter?
I don't
You
know.
have to click on the pencil.
Um, we have. Is it showing up?
No.
Mm-mm.
It did the first time you wrote on it.
That was me.
Oh. Well, how'd you do it?
It showed the pencil and I just clicked it.
Okay, back, Garrett.
Oh,
Garrett is controlling your screen. I guess Haley has to do it.
No!
the only person who can write.
Try it! No.
We will figure this out.
Tyson, try it!
I'm using my tablet. I can't.
Okay, I'm gonna do it then, but we will figure it out because you guys, I want you to do it. That was kind of cool. All right, so
How come I was able to and I'm the only one on the phone?
you're the coolest.
No, I'm not. Shush.
It says I'm controlling your screen, but it doesn't like.
Yeah, I don't know why it's not letting you write. I'm gonna have to explore with Zoom. We'll get better at this. This is only day 2. Okay, so what are they asking us for in the problem? Did y'all read it?
New volume.
New volume, so they want us to find V2. So we're gonna plug in everything else, okay? So somebody tell me P1.
1 atmosphere.
1 atmosphere. Well, let's look at P2 before we fill it in. What is P2?
Torr. Or
800.
895 torrs.
So in your book, that lovely chart that I told you yesterday you needed to know, that is on page 384, you're going to refer back to that a couple times, and that's going to show you your conversion there. So 1 atmosphere is how many torr?
760.
760. So instead of 1 atmosphere, I'm going to plug in 760 for P1. Everybody understand why?
Yeah, because it's the same.
Yeah. All right. So 760 times. What's V1?
5.5.
5.5 liters. Okay. And T1 is 20.
200.
Yes, Caitlin.
290 Kelvin.
298.2 Kelvin. Okay. I didn't put units on the others. Sorry. All right. So number 2 we said was 895. We're trying to find V2. So that's going to be blank. And then our second temperature they give us is 17 degrees Celsius, which I then add 273.15 because it has to be in Kelvin, just like Kason did on the first one. I'm going to get 290.2. Remember, the reason we're getting 0.2, not 0.15, is because of significant figures. We have to round to the 10th decimal place. Okay, so now to get V2 by itself, I'm going to multiply this whole side by the opposite of these. So I'm going to multiply by 290. This is really difficult to do on a laptop. 0.2 divided by 895. And when I multiply that, it's going to cancel, and this is going to cancel. That makes sense? Then I have to do the same thing on this side. So 290.2 0.2 is going to be multiplied by everything on the top over here.
98. Isn't it 298?
No, 290 because I'm using this number.
Oh, you're going from that side.
Yep. So then I'm just doing the same thing to the left side of the equation that I just did to the right side of the equation. So then at the bottom, I'm going to multiply 298 by 895. So in your calculator, it's going to look like parentheses 290.2 times 760 times 5.5, close parentheses, division, open parentheses, 895 times 298.2, close parentheses.
Can you show that like on
Yeah.
your screen?
Can I type it? Ooh.
Yes.
I think you can type it on.
Okay, let's see if it'll let me. Ooh, this is fancy. Okay,
Whoa.
this is
I guess it just doesn't let me type.
okay, I'm just gonna do X for times.
Yeah. Okay. So it's all one question, then you close the parentheses.
Yep, and then division sign, is that on here? I'll just do that. Parentheses, 895 times 298.2. And once you plug that in, tell me what you get.
I got 4.5 liters.
Perfect. All right, 4.5 liters. Did everybody get that when they plug it in that way in their calculator? Yay, good job, Bailey. Good. Stop telling me the internet is unstable. Can y'all still hear and see me?
Yeah.
Yes.
All right. Everybody good with that one?
Yeah.
Let's move on to 11.3. 11.3. All right. I'm going to read it with you guys because we're running short on time. So I want to get through it quickly. If you fill a balloon with air to a volume of 3.21 liters at a temperature of 22 degrees Celsius, what volume will the balloon have if it is stuck in the freezer, -5 degrees Celsius? Assume that pressure stays constant. Someone tell me what equation you're going to use if pressure is staying constant.
Pressure is constant.
Pressure is
V2 over, or V1 over T1, and then V2 over T2.
very good. Thank you. If anything is staying constant, we leave it out. Because it's this is my equation, okay? Now let's just fill it in. So V1, let's fill that in first.
Your V looks like a check. It's cool.
I'm writing with my finger on my mouse pad. Very interesting. All right, so V1, they tell me, is 3.21 liters. Okay. T1 is 22 degrees Celsius, which I add 273.15 to, right? And then I'm going to round to the 10th decimal place and get 295.2. Okay, equals, it's asking me for the new volume, so V2 is going to stay blank. And it tells me it's in the freezer at -5 degrees Celsius. So I'm going to do -5 plus 273.15. Round again to the 10th place, so 268.2. All right, how am I going to get V2 by itself?
You multiply 268.
Good. Got to do it to both sides too. So I'm going to multiply it over here. It's going to cancel, and then V2 will be by itself. And then I'm going to multiply it over here. Let me show you again what that looks like in your calculator when you plug it in. And we should get 2.9164 and so on. So we're going to round to 2.92. And do we remember what our unit is?
Liters.
Liters.
Good. 2.92 liters. All right. Good job. We get to move on to one more thing. I don't know how much time it's going to give me. So if it cuts me off.
I think it gave you extra minutes.
Yeah, there was a message that came across on my end saying this meeting no longer has a time limit.
Oh, wow.
They've been doing that a lot. Because my grandma, she was on a meeting yesterday, and she went like over in it. They said like at the end they were being generous, and they gave her like extra minutes.
Oh,
Yeah, because my friends, their class went for an hour and they got extra time.
well, we can do chemistry all day. Just kidding. We'll do it all day. Okay.
I wouldn't.
Yeah, I gotta
I don't
work
really
in
care. Chemistry's okay.
Oh, well, I'm glad you
As long as I don't have to do math,
Yeah.
It's kind of math.
but it's not
It's
science.
not math, okay?
Fun math.
Yeah.
Yeah.
Glad you guys.
Algebra 2. It's basic.
Yeah.
I can do that. Not
Yeah,
stuff like
you're right. All right, well, let's talk about ideal gases then on page 394 there. So you have to know when you can use this law and when you can't. So to use this law, your gases that you're talking about have to be an ideal gas. And the 3 points there in blue tell you the requirements for an ideal gas. So number one, the molecules that make up the gas are very small compared to the total volume of gas. And number two, the molecules or atoms that make up the gas must be so far apart from one another that there's no attraction or repulsion between them. And then number three, the collisions that occur between the gas molecules or atoms must be elastic. In other words, when the molecules or atoms collide, no energy can be lost in the collision. Also, no energy can be lost when the molecules or atoms of the gas collide with the walls of the container. All right, we're going to talk more about that so that it makes more sense. But basically what you need to know is that gases tend to behave ideally at a high temperature and a low pressure. And if you think about it, it should make sense, because for them to be really far apart from each other, the volume has to be large. And according to Boyle's law, if the volume is large, the pressure is going to be small or lower, right? In the same way, Charles's law says that at a large volume, the temperature will be higher. So it makes sense, high temperature and low pressure, for it to be ideal. And you might be asking, what do we mean by a high temperature or a low pressure? Is 30 degrees Celsius a high temperature? Is 100 degrees Celsius a high temperature? We don't know. So they give us a definition there in the middle-ish of page 395 in blue that says the standard temperature and pressure. They're going to give us a standard to compare to. So the standard temperature would be 273 degrees Kelvin, which makes sense because that's basically what we're adding to our Celsius temperature every time. And a standard pressure of 1 atmosphere. So it's pretty easy to memorize. So we will compare that whenever we're trying to see if gases are an ideal gas. So that will tell us if we can use this equation. So a gas with a temperature that's close to 273 or larger and a pressure that is near or lower than 1 atmosphere will behave in an ideal fashion. So you have to know when you read an equation or a question whether or not your gases are going to behave ideally. All right, so any questions on ideal gases before we move on? Pretty simple. Okay. All right, Dalton's law of partial pressures. This is our next equation we're going to use. So Dalton's law of partial pressures, there at the bottom of 395 in blue, says when two or more ideal gases are mixed together, the total pressure of the mixture is equal to the sum of the pressures of each individual gas. And you can see it there. I'll write it out for you as well. In mathematical terms, the total pressure, which is P subscript T, of a mixture, this is a mixture of gases. So say you have like the atmosphere, you have nitrogen, oxygen, all these gases mixed together. That's your total pressure, equals your pressure of each individual gas added together. This makes sense, right? Pretty much common sense, in my opinion. But you'll see when we apply it. So it just depends how many gases you have. So, and so on is the little dot, dot, dot. But if you had 3 different gases, it would be, you would add up each pressure of each gas, and that would give you your total pressure. Okay, let's see. I'm trying to get out of here. I'm just gonna leave it for a minute. All right, so I'm going to give you an example, and this is on page 396 in your text. Let's get out of that. Okay, so suppose you have 2 steel containers that each contain a gas at a pressure of 5 atmospheres. And let's say that in one container you have oxygen. I'll draw it for you. Would you guys enjoy that? Because I'm so bad at drawing. Okay. So we have container 1, container 2. All right, in this container, each one has a pressure of 5 atmospheres. Okay. All right. And we're going to say that container 1 has oxygen gas in it, which we know is O2. And we're going to say container 2 has nitrogen gas in it, which we know is N2 because these are diatomic molecules. Okay, so Dalton's law says that if we were to take all the nitrogen gas from this container and put it in here, so this is, whoops, this is going over here, then the nitrogen gas, once it goes in here, the pressure in this container, once it's combined together, is now going to be 10 atmospheres. Okay, so that's our new pressure once this is combined. Okay, so let's consider another situation. Let's suppose that each of these containers has oxygen in it. So instead of nitrogen, this is now also oxygen. They are both still at 5 atmospheres of pressure. When we combine them together, the container still has a combined pressure of 10 atmospheres. So what this scenario is trying to tell you is that it doesn't matter what the gas is, it just matters what quantity you have or what pressure you have of that gas. So nitrogen or oxygen, the pressure was the same. So it doesn't really matter the identity of the gas, just how much of it you have. Does that make sense?
Yeah.
Okay, I'm gonna clear this out. And this is a part that I thought was really cool when I studied it, vapor pressure. So if you were to fill a glass with water and set it on the table, what would eventually happen? If you left it there for like a week,
Condensation.
It evaporates.
it would evaporate and you would have no more water in your glass, right? But do you know how it does that?
Or mom would pick it up and put it in the sink.
Yeah, probably so. But the water isn't boiling. So how is the water leaving the glass? Anybody know? This is the part I thought was. It occurs because, remember, we talked about molecules are always moving. So in your glass of water, your water molecules in that glass are moving, right? You just can't necessarily see it. So they're moving, they're hitting each other. Well, some of the molecules will get enough energy to hit the top of your water and bounce out of the glass, which causes it to turn into the gas phase. And evaporation, okay, so evaporation occurs because the molecules are sometimes able to escape from the surface of that liquid if they have enough energy to do so. So once they hit each other enough times, get enough energy, they bounce out, and then they're on the surface of the water there. So vapor pressure is the pressure, you'll see it in blue on page 396. It's the pressure exerted by the vapor that sits on top of any liquid. So in other words, any container of liquid has gas floating on top of it, which I thought was kind of interesting. And the pressure that it's exerting on its surroundings is called vapor pressure. So we're going to talk about vapor pressure. And I'm moving on to 397. The vapor pressure of any liquid depends on the chemical nature of that liquid. So for example, gasoline has a very large vapor pressure because it evaporates easily. On the other hand, water has reasonably low vapor pressure because it does not evaporate very easily. What you may not know is that the vapor pressure of any given liquid also depends on its temperature. So you'll see that table there, 11.2 on page 397. We're going to use that a couple times. That is the vapor pressure of water at different temperatures. So as you'll notice, as the temperature rises, the pressure rises. So higher temperature, your vapor pressure is going to be higher. And the vapor pressure, it's not only true for water, it's true for any liquid. So any liquid, if the temperature increases, the vapor pressure is also going to increase. Okay, so look at the temperature on the chart at 100 degrees Celsius. What is the vapor pressure there for water?
760.
Yes. Does that number look familiar?
A torr or an atmosphere.
Yes, yes. So that is the same as 1 atmosphere, which is normal atmospheric pressure. So the temperature 100 degrees Celsius should tell you something too. That's water's boiling point, right? So it's not a coincidence. The true definition of a boiling point is the temperature at which the vapor pressure of a liquid is equal to normal atmospheric pressure. So that's why you'll see that it's equal to 1 atmosphere when it's at its boiling point. And I'm sure you've heard before that water boils at a lower temperature at higher altitudes, right? And this tells you why, because the atmospheric pressure is lower at a higher altitude, which means the temperature for water to boil is going to be lower. Kind of cool. All right, so I'm moving on to page 398. And we'll do an example in just a minute. So when you read a question, which we'll do in just a moment, and it's talking about a chemist making a gas in the presence of water, we call it collecting gas over water or collecting gas in the presence of water. Whenever you see one of those phrases in the problem, you have to realize that the gas collected is a mixture of the gas with the water vapor, because you have water vapor and you have the gas on top. So to find out how much gas is produced, you have to use Dalton's law, which is the law we just talked about that talks about the total pressure is the pressure of each individual gas added up together. Okay, so we're going to do an example in 11.2. Is everybody good to go ahead and do this example and then 11.4 and then be done?
Yeah.
Okay, cool. All right, so 11.2, a chemist produces hydrogen gas in an experiment and collects that gas in the presence of water. So there's that phrase, he's collecting gas in the presence of water. If the total pressure of gas collected was 1.115 atmospheres and the temperature was 26 degrees, what was the pressure of hydrogen gas collected? Okay, I'm going to share screen so you can see, even though your book tells you, I like to do it too. All right, so the problem tells us he's collecting gas in the presence of water, which means it's actually a mixture of hydrogen gas and water vapor. So Dalton's law tells us that the total pressure, as you'll see there, is the pressure of hydrogen, right? Plus the pressure of the water vapor. I'm just going to put WV. Okay? And the problem tells us what the total pressure is. It said it's 1.15. Whoops. 1.115 atmospheres. And it tells us one other thing. Does it tell us a pressure of hydrogen or water vapor? No. It does tell me the temperature. Based on one page back, table 11.2, if we have the temperature, we can find the pressure of the water vapor, right? So it was 26 degrees. So I'm looking at 397 at table 11.2, and I see that the pressure at 26 degrees Celsius is going to be 25.2. So I'm trying to find the pressure of hydrogen. And then based on my chart, I can fill in 25.2. However, this is a different unit. Hi. This is a different unit. So what my 25.2 is in what? Is it atmospheres?
Torch.
Torrs.
Yeah.
So I need to,
To,
what, Haley?
was it Tor? Yeah, it's Tor. Okay.
Yeah, it's
Sorry. You glitched for a little.
Oh, I'm sorry. Yes, it's torrs. So we need to convert either the atmospheres or the torrs. Doesn't matter which one. But in the problem, it looks like they convert the torrs to atmospheres. So we're going to convert this number to atmospheres. So we'll go 25.2 torrs is our given value, right? Do y'all miss conversions? No, you do. Okay, over 1 times my conversion factor, which I'm going to use that one chart I told you on page 384. You want to go ahead and mark that because you're going to use that a bunch. So on that chart, it tells me that 1 atmosphere, 1.000, if you really want to be technical, atmospheres, equals 760 torrs. 0.0. Okay. All right, so we are going to put that in the calculator. And in the calculator, really, this is all I have to put because, whoops, sorry, I'm trying to do it. Okay, I can really just put it like this because my ones don't really matter, do they? 25.2 divided by 760. That's all you got to do in your calculator. And that should give you 0.0332 atmospheres. So now I can plug it back in my equation. So I'm going to just erase on the top so you can see. Okay. All right, so now I'm going to plug it in up here, which is going to be 0.0332 instead of this number. And to get pH by itself, I'm going to, since I'm adding here, do you see the plus sign? I'm going to subtract. So I'm going to subtract 0.0332. Which is going to get P by itself over here. And then I'll do the same thing on the other side, of course, which is going to give me 1.082 atmospheres. And that is the pressure for hydrogen in that example. Did y'all have any questions on how we did that? No? All right, let's do 11.4 and then we will call it a day. In your student book, 11.4. Haley, you want to do this one? No, she doesn't.
No. It's also going to be hard for me to write on my tiny, tiny screen.
Yeah. I'm just kidding. All right, 11.4.
You know how small my phone is, so.
All right, we'll do it together. Okay, so it says a chemist collects carbon dioxide over water. There's your phrase, he's collecting a gas over water. The pressure of gas in the collection container was 861 torr. If the temperature was 22 degrees Celsius, what pressure of carbon dioxide was collected? Okay, so the mistake I made when I first did this on my own was that I was putting the 861 torr in the wrong place in the equation. The 861 torr is the total pressure or the pressure of one of the gases. What'd you say?
I thought.
Is it total pressure? See, I'm gonna have to add up all my pressures, which would be carbon dioxide and
It's part of the gas, I thought.
see, that's what I thought, but it's not.
But it's also a total?
Nope, it's just the total. It's just the total. So if you look here, it makes sense. I've got my total pressure, I've got my pressure of carbon dioxide, and I've got my pressure of my water vapor. So they are asking me for the pressure of carbon dioxide. It says, what was the pressure of the carbon dioxide? So I'm not gonna know this number. So it has to be either this number or this number. Well, it's not the pressure of water vapor because it says it's the pressure of gas in the collection of the container. So that means it's the total pressure. So 861 torr is the total pressure. And that's gonna equal the one I wanna find plus the water vapor pressure. How am I gonna find the water vapor pressure? They just give me a temperature.
Go to the table.
Yep.
11 or 11.2.
Yep, table 11.2.
19.8.
Good. And that's already in torrs, so I don't have to convert. Okay. Now all I'm doing to get this by itself is subtracting 19.8 from both sides. Okay. So 861 minus 19.8 should give you 841.2. Because of significant figures in the problem, 3 is what I've got. So I'm going to round that to just 841 torr. That is the pressure of the carbon dioxide. Any questions? All right. Y'all have been an amazing class today. I think today went better than yesterday, especially because there was more of you here. I'm happy. And we will continue on with Module 11 tomorrow.
How do you think if Raekwon ever came into these classes, you know how if he's never here and we always get a whole lot done?
Yeah.
How do you think that's gonna go when he comes here?
Well, we might not get a lot done, but it will be fun.
I think we're all gonna be sending memes. That's like when he comes, he needs you, so then you plan, okay, that day we're not gonna do anything.
Exactly. I never know when he's gonna come though. He's like a toss-up. He might show up, he might not. Who knows?
It's to do an RSVP.
Yeah, there you go. All right. Well, I'm signing off. I'm gonna go ahead and post this on YouTube, hopefully, because I love seeing my face on YouTube. Just kidding.
You got one subscriber.
See ya.
Okay.
Bye.
Y'all have a good day.
Bye.
Bye.